In this lesson, we're going to examine the properties of organic molecules. And this is a review of topics from grade 11. We are going to apply the intermolecular forces ideas to our organic molecules and review the properties of melting point, boiling point, and solubility, and how they apply to organic molecules. We'll then be able to compare these properties among a group of organic molecules, or be able to identify organic molecules based on the properties that they have. Now, most importantly, we need to review the intermolecular forces so that you can feel comfortable identifying what type of intermolecular forces will exist between organic molecules. Remember, when we're looking at our intermolecular forces, that we're looking at the forces that hold the molecular compounds together. There are three main types of intermolecular forces: London forces, dipole-dipole forces, and hydrogen bonds. With London forces, these are the types of forces that exist when we have nonpolar molecules. So when we have two nonpolar molecules, what happens is the electrons randomly shift in one molecule, making a slightly negative end to the molecule. This leads to a charge separation in a neighboring molecule, where the electrons in this molecule will move away because they repel the electrons in the neighboring molecule, leaving a charge separation within the molecule, and then there's an attraction from the slightly negative end of one molecule to the slightly positive end of another molecule. These forces are very, very weak, and they are formed and broken very, very easily, and therefore they will lead to weak intermolecular forces. Dipole-dipole forces are a type of intermolecular force that exist in polar molecules. And what happens when you have a polar molecule is you have a permanent dipole. So what that means is that when you have a polar bond within the molecule, so for example, a CO bond that has a dipole on it, that dipole on one molecule can be attracted to the dipole on a neighboring molecule, because there's an attraction between the slightly negative end of one of the molecules to the slightly positive end of the other molecule. Now, hydrogen bonds are the strongest of these three types of intermolecular forces, and will also occur when we have a polar molecule. They're a little bit more specialized though, because what we need in order for a hydrogen bond to occur is we need a slightly positive hydrogen atom, and we need a lone pair of electrons on either an oxygen, a nitrogen, or a fluorine. So in organic chemistry, one of the functional groups that we have that would be important to consider here in terms of hydrogen bonding is the OH group. When we have alcohols, we have OH, and the OH is a polar bond, which gives us a slightly positive hydrogen, and then we've also got a lone pair on our oxygen. So what we can have is we can have a neighboring molecule with this same functional group, and the hydrogen bond is the attraction between the lone pair of electrons on the oxygen and the slightly positive hydrogen in the neighboring molecule. Because this is an attraction between electrons, which are negative, and a slightly positive hydrogen, it's stronger than a dipole-dipole force. Remembering that this is an attraction between a slightly positive and a slightly negative. Now also, an important point is that all molecules will have London forces. So because these arise from electrons randomly shifting, in any molecule we can have those electrons randomly shift. And so London forces do exist in all molecules. When discussing intermolecular forces, we tend to focus on the strongest of the three. So for example, if hydrogen bonds are possible, then we tend to focus on their existence. If dipole-dipole are possible, then we tend to focus on their existence. And if only London forces are possible, then that's what we focus on. Now, one of the big advantages of studying organic molecules and their properties is that there are very few bonds that we deal with. So what we can do is just look at the most important bonds in the organic molecules and know whether or not they're polar or not. The easiest one is the CH. The difference in electronegativity between these two atoms is too small. So this is a nonpolar bond. With these bonds listed, the OH, the CO, the NH, the CN, and the CCl bond, they all have a difference in electronegativity between 0.5 and 1.7. And you'll remember from studying bonds that this means that these are polar bonds. It's also important to know the direction that the electrons go. So recall that they go towards the more electronegative of the two atoms. So I'm showing here what direction they will go. So nitrogen and oxygen tend to be more electronegative than other atoms that they bond with. And between chlorine and carbon, the chlorine is more electronegative. If you know the identity of these polar bonds, it'll be much easier for you to be able to predict and know the type of intermolecular forces, and then an extension of that, the properties of organic molecules. Really, what we need to identify is where hydrogen bonds are possible. If we know where hydrogen bonds will be possible, and we know when we have nonpolar molecules, then we'll know what's left over will give us dipole-dipole forces. The two main bonds that are important when identifying the presence of hydrogen bonds are the OH bond and the NH bond. The presence of these will lead to hydrogen bonds because they have what it takes in order to form a hydrogen bond. We've got our slightly positive hydrogen, and on the oxygen and nitrogen, there's a lone pair available. So therefore, if you look back at the requirements, you'll see that having these bonds present will lead to the formation of hydrogen bonds. Molecules that have C double bonded to O, like aldehydes and ketones, will form dipole-dipole forces. And molecules that only have carbon and hydrogen, such as the hydrocarbons, will only have London forces. They will be nonpolar molecules because the only bonds that are of concern are the CH bonds, which are nonpolar. This chart summarizes by family the polarity and in turn the intermolecular forces for each of the different families. So for the hydrocarbons, as we discussed, because the only bonds within them are CH bonds, they'll be nonpolar molecules, so the intermolecular forces that they will have between them are London forces. When you have alcohols, they have the functional group of OH, which is a polar bond, leading these to be polar molecules, and because it's OH, we can accommodate hydrogen bonds. With ethers, the functional group is the single bonded oxygen, and this lies in the middle of the chain. So although this is a polar bond, and these molecules will be polar, they cannot accommodate hydrogen bonds because there is no slightly positive hydrogen. So therefore, they will have dipole-dipole as their intermolecular forces. For aldehydes and ketones, they have the carbonyl carbon, which is a polar bond, but again, they don't have a slightly positive hydrogen within the molecule. Therefore, they're polar, but have dipole-dipole forces. Carboxylic acids have, at the end of the chain, the carboxyl group, which consists of a carbonyl and a hydroxyl. And this is polar. It can accommodate hydrogen bonds. So you've got the OH group. So if you've got two different carboxylic acid molecules, they can be attracted to one another through hydrogen bonding. Now, this comment here about them being able to ionize in water, we'll discuss a little bit later when we discuss the solubility of carboxylic acids. Ionize simply means breaks up into ions. For esters, recall that they have this COO group, but they have it in the middle of the chain. So again, we don't have a slightly positive hydrogen that will be available to accommodate hydrogen bonds. These also tend to be quite bulky molecules. So because the polar bits of the molecule are in the middle of the chain, okay, this is going to affect some of their properties. For example, they're not going to be very soluble despite their polarity. Amines have nitrogen in them, okay, and they will often have NH bonds. So they will be polar because of the NH bond, and they also have what it takes to accommodate hydrogen bonds. Amides, like esters, have the C double bonded to O, and in place of the oxygen, they have a nitrogen. So what happens in this case is, again, we have these bulky molecules that do have polarity. They're going to have low solubility because of their bulkiness, which we'll discuss a little bit later when we look closely at properties. So let's look at the two main properties we want to examine. We want to be able to identify or compare the boiling point and melting point of organic molecules. And we will also look at their solubility. Firstly, we'll look at the boiling and melting points. Recall that when we want to boil or melt something, we need to be able to break intermolecular forces. So the greater the intermolecular forces, the higher the boiling point or melting point, because we'll need more energy in order to break those intermolecular forces. Now, there are 3 points to consider. The first point is that we can compare molecules that have different lengths of chain. So if I compare these two alkanes to one another, and I want to examine their relative boiling points, what I'm going to do is look at the length of the chain. Both of these are alkanes. So at the end of the day, they're both nonpolar molecules, but because they're different, they're going to have different strengths in terms of their intermolecular forces. As you can see by looking at these molecules, the longer the chain, the more opportunity there is for London forces and interaction. So this molecule here is going to have a higher boiling point. There are more London forces, so there are going to be greater intermolecular forces, and it's going to require more energy to break them down. The other thing to consider is isomers. So if we have the same number of carbons, but we have different arrangement of the atoms in the molecule. So I'm looking at 6 carbons here, and I've got one that's a straight chain alkane and one that's a branched alkane. The one that's branched is going to have fewer opportunities for interaction. So straight chain hydrocarbons will tend to have a higher boiling point. Now, another point to consider here is that this rule about the length of the chain and the branches in the chain will have the same impact if I change the family. So if I make both of these alcohols by attaching an OH group and both of these alcohols, they'll still be part of the same family. So they would be two molecules part of the same family. If they're both alcohols, they can both have hydrogen bonds, but the one with the longer chain is going to have the higher boiling point. The same thing here. I can change these both to aldehydes, and the one with the straighter chain will have the higher boiling point. So what you're going to find when you compare molecules is you're either going to compare molecules that have the same length of chain and a different functional group, or they have the same functional group and they have either a different length of chain or different branching within the molecule. You're not going to be asked to compare two things at the same time. Now, one last thing to consider is when you're comparing hydrocarbons. So if you compare an alkene versus an alkane, the alkanes have more hydrogens in them. You can almost think of the hydrogens as being like tendrils that are able to reach out and attract to the other molecules. With the alkenes, they have fewer hydrogens, so there's fewer points for attraction between the two molecules. So in this case, the more saturated ones will have a higher boiling point. Now, when we're comparing solubility, the focus is to look at solubility in water. And a reminder that water is a polar molecule. So therefore, when we're looking at solubility, we're looking for how polar a molecule is and its ability to be able to interact with water. The more favorably a molecule can interact with water, the more soluble it's going to be. And we also want to look at water's ability to be able to surround the molecule. So lengths of chains are going to be important in addition to the families that we're looking at. So this is when the type of intramolecular force is really important. When we look at something like an alcohol that has an OH group, we know that things with an OH group can hydrogen bond. And because they can hydrogen bond, they'll be able to hydrogen bond to water as well. And so water will be able to surround this and dissolve it. When we look at an alcohol that has a longer chain, however, the solubility is going to decrease. Because when we look at this, water can effectively surround the OH and form hydrogen bonds with the OH, but the rest of the molecule is nonpolar. So the longer and more complex the rest of the molecule becomes, the lower the solubility. Also remember that nonpolar substances will be considered to have very low solubility in water. So all of your hydrocarbons, which are nonpolar, will be considered to have very low solubility in water. As I said before, we would discuss carboxylic acids a little further. Carboxylic acids have a carboxyl group, and they are actually able to ionize or break up into ions when they are put into water. So what will happen is we'll produce a negative ion and we'll produce a positive ion. Now, although this won't happen to the same extent as it will in an ionic compound, for example, sodium chloride breaks up really, really well in water, it won't break up as well, but it'll still produce these ions, and its ability to ionize will make it quite soluble in water. Because as you know from your previous studies of properties, Ionic compounds tend to be very soluble in water because of the attraction to the negative ion and the attraction to the positive ion, and water's ability to surround these ions. Much like our discussion over here, though, as the chain gets longer, that solubility is going to decrease. Now let's look at some examples. First, we'll compare the boiling points of these four molecules. And as I said before, you'll notice that you're comparing molecules that have the same length, or we've got two molecules here that are from the same family, but they're different lengths. The first thing that we want to do is identify, based on the family, what type of intermolecular forces they have, so that we can decide which one will have the strongest and which one will have the weakest intermolecular forces. Pentanol, because it's an alcohol, has the ability to form hydrogen bonds. Pentane and butane are both nonpolar molecules, so the forces that hold them together are London forces. And pentanal, which is an aldehyde, is held together with dipole-dipole forces. So if we want to put these in order from lowest to highest boiling point, that means we want to start with the weakest forces. The weakest are our London, and so we want to compare butane and pentane. Because butane has the shorter chain, it will have the lowest boiling point. Pentane being next, with slightly more greater London forces, because there are more electrons and more possibilities for interaction with the longer chain, it will have a slightly higher boiling point. Next on our list, we would expect to see pentanal. Pentanal having dipole-dipole forces. They're a little bit stronger than the London forces holding pentane molecules together. And finally, we would expect pentanol to have the highest boiling point because of its ability to hydrogen bond, which is the strongest of the three types of intermolecular forces. Now, I'm not going to write out the explanation. I've kind of said it verbally, but it's very clear here that you need to justify your choice using proper terminology. So you need to explain why you've put these in order using proper explanations of the different types of intermolecular forces and their strengths. With this next group, okay, we want to look at lowest to highest solubility in water. So again, we want to identify the polarity and the types of intermolecular forces. Butanal and octanal are aldehydes, and they have the ability to form dipole-dipole forces. They are polar molecules. Butane is nonpolar and has London forces. Octanal, as I said before, also dipole-dipole. And then butanoic acid is a carboxylic acid, so it has that Cu group. It can form hydrogen bonds. And also, because we're talking about solubility, it's important to note that it can ionize. Because the butanoic acid can ionize, that's going to put it with the highest solubility. Its ability to hydrogen bond is also quite helpful, but it is important to state that it does ionize because that increases its solubility significantly. The one that's going to be lowest on our list is butane because it's nonpolar, and nonpolar substances are not soluble in water because they have no effective way of interacting with water molecules or being surrounded by them, which is required for dissolving. Between butanal and octanal, as the chain length gets longer, the solubility is going to go down. So in this case, the octanol is next on the list in terms of low solubility. Butanol, which is polar, is going to have higher solubility than octanol, which has a longer chain and is also polar. So that concludes our review of properties and their connectedness to organic molecules.